Hello everybody, we hope you enjoyed the previous lecture on the solid removal of settable solids. In the previous lecture, we've talked about different box design that could minimize the accumulation of settable solids in a box and how inefficient designs could lead to excessive labor costs. In this lecture, we will now focus on the solid removal of suspended solids. So if you recall, suspended solids are solids that do not settle down within an hour. So in theory, these solids will be floating around the water, able to be removed from the box. So once they exit the box, we will then go through another process in which we call the mechanical filtrations. The technologies that are used for suspended solid removal often rely on what we call sieving, or in other words, mechanical filtration. Based on the particle size, we can break down the traditional filtrations into conventional particles filtrations, microfiltration, ultrafiltration, nanofiltration, and even reverse osmosis for very fine particles. The design criteria for any suspended solid remover is to have a good understanding of the type of solids that you will be accumulating. Sometimes, if you have an incorrect diet formulation, it will cause the liquid feces to remain in the suspended solid form instead of a settable solid. And you would require a very fine mesh to sieve out all of these liquid feces. Technologies that are currently used to remove the suspended solids are very similar. They all utilize what we call a filter media to remove away the remaining suspended solid. One good example is this setup over here we have on the right, in which we have a beaker filled with liquid and suspended solid. As you pour them through a piece of filter paper, what you can get is the clear liquid. So traditionally, this is what we have been doing for the filtration process. There are several technologies that exist in the market to control suspended solids. The first being the most commonly drum filters. The second will be what we call the media filters, which are sand filters or any equivalent filters. And these are additional, not so common technologies like tube settler, cartridge filter. And lastly, we have what we call a foam fractionation. We will cover foam fractionation on a separate lecture because due to its unique characteristics. We will now look into the theory of applications for a drum filter. Drum filter is widely used in the RAS systems. The liquid is to be filtered and discharged by gravity into the drum, and the perimeter of the drum is covered by a mesh, so impurities larger than the perforations are trapped inside of the surface while clean water will exit. The typical design criteria is to understand the pore size, the flux, the type of suspended solid size, and whether is it a freshwater or saltwater application. So what we have here, we can see here is how a typical drum filter looks like. As you can see, dirty water will enter the drum filter via the center, and the drum slowly rotates while the clean water is filtered out through this mesh. Any filter eventually will clog up over time. However, the drum filter has a continuous cleaning method, as the drum filters are backwashed with a high water spray using from the filtrate. So sometimes auto trigger can also be activated using water saver in the drum. So I'll now show you a quick animation of how a drum filter looks like. Water will enter the drum filter in the middle, as explained earlier. As the drum rotates, it builds up what we call a filter cake. So this filter cake will accumulate on the side of the wall, while clean water will pass through the drum and being filtered. So firstly, it is important to control the pore size of the drum, as different pore size will give you different filtering capabilities as well as different flux. We earlier mentioned that drum filter has a continuous cleaning action, and it is achieved using soap. As the filter cakes are being built up on the side and carried up vertically, water that is being filtered is used to backwash some of this filter cake buildup, and the filter cake will be removed as a slurry. So this is what we call a continuous cleaning process, where some of the water is being used to backwash and carrying out all the dirty solids. The first important part of the drum filter sizing is to understand this. A smaller pore size will give you a lower flux, and you have to probably backwash this more frequently. However, a larger pore size will give you a higher flux, but you are not able to filter small particles. So understanding of the type of solid that is expected in the system is important, as it will determine your pore size, which will give you the corresponding flux, and from there you will estimate how much filter you need. Drum filters is commonly used in the aquaculture industry, especially in the fish industry in a saltwater process. However, do note that drum filter is usually more expensive as compared to the traditional media filter. There have been debates going on the benefits of using drum filter and the cons and using drum filters. One of the cons of using drum filters with formulated feed is sometimes formulated feed tends to disintegrate when they are rotating in the drum, and further aggravating your suspended solid issue. We will now move on to the next part, which is utilizing media filters for suspended solid treatment. Number one, it is definitely cheaper as opposed to drum filter. And the theory of operations is relatively simple, in which you pass the water filled with suspended solid through a packed bed media, which can be filled with sand. The way how you distribute the sand can be done in different manners. You could use the coarser sand at the bottom, followed by the medium sand and the finer sand on the top. Due to the pressure loss across the media filter, sometimes you will require a pump to pump the water through the media filter, which is unlike the drum filter, which do not have excessive pressure loss. Sometimes solids will tend to accumulate at the top of the sand filter, and you will require a backwash to remove away the accumulated solids. In each sand filter, you require different sand size distribution for efficient backwashing and filtration. So in our case, we have shared with you the type of sand size distribution we are utilizing in our system. The sand filter volume is about 1.1 meter cube, and 72% of it is what we call the fine sand of 0.6 mm to 1.2 mm, and 12% of it is sands that have diameter from 1.2 mm to 2.4 mm. The largest type of sand distribution we have is from 2.4 mm to 4.8 mm, which accounts for about 16%. It is important to know how to design your sand size distribution. An easy way to do this is to go talk to your local water filtration manufacturers or water filtration systems designers that typically design your cartridge filter and your household sand filters to help size your sand accordingly. Alright? And it's also important not to use the fine sand for all of the sand filter, as when you tend to backwash, there is nothing to hold back the fine sand. In our case, the coarse sand is actually located at the bottom, followed by the medium and the fine sand at the top. Operating the sand filter would require some tricks and knowledge, as the sand filter is not like a drum filter in which it utilizes what we call a continuous cleaning. Suspended solids that are trapped inside the sand filter has to be removed from the system, and the removal method is to execute what we call backwashing. On a daily basis, we have to backwash at least once to ensure that the particulates that are trapped do not start decomposing into the system and further deteriorating your water supply. We do a backwash of at least 60 seconds to ensure all trapped particulates are removed. However, by doing backwash on a sand filter system, you usually tend to use system water to perform some sort of backwash, which for some of us can be quite costly, especially if you are located far from the coast. So one way of doing it is to change the piping, in which when you're about to backwash, you will swap the piping into a freshwater line and use freshwater to backwash. Because a backwash up to 60 seconds would sometimes reduce salt water by at least 500 to 1000 liters, and the salt needed to bring back to the original salinity will take 4 to 5 kilos. So depending on who you're buying the salt from, the cost can range up to half a dollar to $2. So that's all for suspended solid. In the next lecture, we will talk about foam fractionation, which is a specific technologies that are used to control suspended solid as well as removing organics.